Hello, welcome to my talk all about the fluids. This talk is on an interesting and important topic. Is the Navier-Stokes equation correct? We all know very well that the Navier-Stokes equation is correct as the universal governing equation for fluid motion, since numerous examples have confirmed it. However, some research works have shown there are some inconsistencies behind Navier-Stokes equation. For instance, the Cauchy symmetrical stress tensor have been fully adopted to fluids nearly 200 years ago, but it is required for fluids, or it is correct for fluid. In this talk, I will show you what are the inconsistencies behind the Navier-Stokes equation, and the examples for illustrating the inconsistencies include some from the textbooks. Is the Navier-Stokes equation correct? The answer for this, yes and no. For yes, that's because the Navier-Stokes equation as the governing equation for fluid motion have been proven by numerous examples, experimental data, analytical solutions, and numerical simulations. For no, that's because there are still some inconsistencies behind Navier-Stokes equation, specifically on the symmetrical stress tensor for fluid. It is well known the Cauchy symmetrical stress tensor was originally developed for the elastic material, the solid, and then fully adopted to the fluid by Cauchy himself. But how we can explain exceptions for the asymmetrical stress tensor found in real fluids? Is this Cauchy's law for angular motion also a prerequisite for fluids? Can we have a different way to derive Navier-Stokes equation? In this talk, I will answer all these questions. First, let us look at a simple classical flow, the Couette flow. The Couette flow is confined between two large parallel plates. The lower plate is fixed and the upper plate moves at a constant speed at a distance h. The move speed of the upper plate is assumed small, so the flow confined between these two plates is nominal. So based on the analysis of the problem, we can see the velocity component v and w are 0, and the u is the function of y only. As such, the Navier-Stokes equation can be simplified to this simple partial differential equation. Apply the boundary condition, we found the solution. This is a very simple flow. From the plot, we can see the flow velocity increases linearly with y. In this slide, we are going to look at the shear stress in the classical Couette flow. From the Cauchy's symmetrical stress tensor, we can easily calculate the horizontal shear stress tau12 as this. And from the requirement of the symmetrical stress tensor, a vertical shear stress tau21 is calculated like this. They can be seen both horizontal and the vertical shear stresses are non-zero. If we look at this, based on the symmetrical stress tensor, we have tau12 equals to tau21, and the tau prime 12 equals to tau prime 21. We'll go back to the definition of fluid. From the fluid definition, it states a fluid cannot bear any shear stress at rest, and under shear stress, the fluid flows in the direction of the applied stress. From the definition, it is easy to understand the horizontal shear stress tau 1, 2 because we have the horizontal flow in the Couette flow. But for symmetrical stress tensor, there must be a non-zero vertical shear stress tau to 1. However, why this vertical shear stress does not cause a vertical flow? If from the fluid definition in the Couette flow, it can be concluded vertical shear stress tau to 1 is 0. The shear stress tensor in this case would be asymmetric, i.e. tau 1, 2 is not equal to tau to 1, since in the flow tau to 1 is non-zero, but the vertical shear stress tensor is 0. There may be an argument in the Couette flow there is a vertical shear stress. That's because the upper plate stops the flow moving in the vertical direction. The answer for this is no, because in reality, whether there will be flow flowing out from the opening totally depends on the pressure of the flow between the plates. If the flow speed is large enough, there might be a suction of the flow in the opening instead of the flow flowing out. Look at this example. In this example, we do have two openings, the small vertical tubes. If there is a vertical stress tau to 1 in the pipe, then there must be vertical flows in the tube, regardless of the height of the tube. Obviously, this is not true. The height of the flow in the tubes totally depends on the pressure of the flow in the pipes. Now we look at the situation for a shear stress applied on an element as seen in the figure. And we will see what will happen if the element is a solid and if the element is a fluid. If the element is an elastic material, for instance a solid, under the shear stress tau to 3, there will be a deformation of the element. However, due to the elasticity of the element, there will be a shear stress tau 3, produced to balance the applied shear stress, and tau 3 equals to tau 3. This is required by the Cauchy's symmetrical stress tensor. And if this element is a fluid, the applied shear stress will cause the flow of the element from the definition of the fluid. And because of the flow, a fluid friction is induced to balance the applied shear stress. Hence, in this case, there will be no shear stress pair to balance the applied stress in fluid. Here are some examples for the inconsistencies of the symmetrical stress tensor introduced. Kondo's book, Flow Mechanics, page 126. There is a statement: the stress tensor symmetry is violated in the electric field on polarized molecules, where anti-symmetrical stresses must be included in the analysis. Another example is the Wilcox book, Turbulence Modeling for CFD. On the page 39, there is a statement: the symmetrical stress tensor is for simple viscous flow, but not for some anisotropic liquids. There is no reason for the statement. Therefore, there will be a question. If Cauchy's law of angular motion is universally correct for fluids, what exceptions we have as above? We never see any exceptions for Newton's laws of motion. As we know from the Newton's definition of fluid friction, the fluid viscous force is caused due to the different fluid speed at two joint spatial locations. Here, we'll take two neighboring points in the field, A and B, and their relative velocity at a certain time is calculated here. For the point A, its position and velocity are given as this, and B, the neighboring point, its position and velocity can be simply expressed as the position and the velocity of point A plus the small increment such as delta x, delta y, delta z, delta u, delta v, and delta w. For the relative increment, it is given by this. The velocity vector increment can be expressed as this, and this is the dot product of the strain rate tensor and the relative position vector delta r. Here we can see the strain rate tensor is not symmetrical. Based on the strain rate tensor, a new fluid friction tensor can be defined as this. This can be also called the fluid stress tensor, but it is different from the normal symmetrical stress tensor. This tensor is based on the Newton's definition of the fluid friction. It is from the strict physical analysis for the different velocity between two neighboring points in fluids. Asymmetry for the stress tensor is not required here. From the stress tensor, the fluid stress force on a unit surface is calculated as this. In a plot, the stress force on a unit surface is given by this. From the stress force on a unit surface, it can be seen stress force in x direction, Fx, is caused due to the increment of the velocity component, u only, and the increment can be in all x, y, or z direction, as seen in the differentiations with regard to x, y, and z. Similarly, we have the stress force in y and z directions, Fy, Fz, are only related to the corresponding velocity component increment of v and w. Now we look at the special surfaces of a cube, S1, S2, and S3, on which the normal vectors all have only one component. That's on S1, M1 equals 1, and N2 and 3 are 0. So the force on the S1 has 3 components, and same on S2 and on S3. So if we draw this stress force component on the surfaces, we can have the drawing as this. So from this drawing, it can be seen that the new stress tensor has a better physical significance than that of the symmetrical stress tensor. For example, we can see the stress force acts in x direction on a surface of a constant y. So you can see the x direction because of the velocity increment on the y surface here. Now we look at the total stress tensor. This is very similar to the symmetrical stress tensor. The total stress tensor contains basically three terms: the term from the pressure, the term for representing the fluid compressibility, lambda is the second viscosity coefficient, and this is the fraction stress tensor. But here, the fraction stress tensor is not symmetric, and the divergence of the total tensor is given by this. Now we look at the last three terms for each component in the divergence of the total tensor, and also apply the new defined stress tensor. So we have the equation as this, and this, and this for velocity component u. Similarly, we can calculate the last three terms in the second component of the divergence of the total tensor, and the third term as this. Now we consider the incompressible flows. So put all this together, we have the moment equations for the incompressible flow. Write this in a vector form. It is this. And you can see from here, the substantial derivative is used in this way. For the compressible flow, the moment equation can be derived from the transport theorem with the assumption of the second viscosity coefficient, lambda, as 1/3 of the fluid viscosity, mu. Write this equation into the vector form. So we have the moment equation for the compressible flow. This same equation as the moment equation in the Navier-Stokes equation for compressible flow. We have discussed the symmetrical and asymmetrical shear stress. The symmetric strain rate tensor can be divided into symmetrical and antisymmetric strain rate tensor as this. The first part, the symmetrical strain rate tensor, was actually employed by Stokes in deriving the fluid dynamic equation. The component of the strain rate are symmetric. The second term is the antisymmetric strain rate tensor, which corresponding to the rotation motion of the fluid, with the rotating component omega 1, omega 2, and omega 3. The vector omega is half of the core of velocity vector, as this. It can be understood in the original Navier-Stokes equation, the rotational motion have been excluded in deriving the fluid dynamic equation. The rotation motion might not cause the shear stress in solid, but this is not correct for fluids. We will see this in the next slide. In this slide, a discussion will be made for the difference between the solid and fluids regarding the pure rotational motion, whether they should be included in the stress tensor. Now imagine a rotating circular cylinder as in the drawing. If the rotating cylinder is a solid and the cylinder rotates around its central axis, Obviously, there will be no shear stress acting on the solid. Therefore, it is reasonable if the rotational motion is excluded in calculating the shear stress in solid. However, if the rotating cylinder is full of the fluid and rotate along its central axis, this would be a special Taylor-Couette flow for which R1 equals 0 and omega 1 equals to omega 2. The flow in the cylinder will eventually rotate with the cylinder. Since the different velocity exists between two different radical points, as seen here, U1 and U2, therefore, there must exist a fluid friction in the rotating flow. In this regard, the exclusion of the shear stress due to the pure rotation motion in the fluid is not correct.